Okay, so this is lecture number 33 of EE 503. So in the last lecture, lecture number 32, what we have studied is linear minimum mean square error estimation. Okay, so in this problem setting, this is the summary of our earlier results. X is a random vector, which is the observation vector. This is a random vector. Y is a desired random variable, and we would like to estimate Y from X. Okay, from the observations, we would like to map these observations to a Y estimate. Okay, so for the linear MMSE estimation, the estimator is fixed. Estimator is fixed as a linear combiner. So you may say that this is like a parametric estimation. So W vector contains the unknown parameters, and this is just linear combination of the elements of the vector X. Okay, that is the inner product. So what is our goal? We would like to set these W's such that mean square error, deviation of Y hat from the true value of Y should be minimized on the average. What do I mean by on the average? If I take, average overall expectation, average or expectation overall observation vectors and desired quantities. Okay, I would like to minimize this mean square error, but under a constraint. Now my estimator is a linear estimator. Okay, under this constraint. Previously, we didn't have this linear estimator constraint, and we have found minimum mean square error estimator. That's a nonlinear estimator in general, and that estimator corresponds to, you may remember, the conditional mean operation. Okay, for the linear estimator, last time we have derived this equation. So optimal weights satisfy this equation system. Okay. So today we will be starting from this point and we will solve some examples. So what is Rx? Rx is the autocorrelation matrix of observation vector, which is something that we have studied, for many weeks or so. And what is Rxy? This is the pairwise cross correlation of each observation and desired random variable. So this X vector times Y. So this is for, let me write it with a different color. This is, this part is for real valued, let's say, vectors. So I'm assuming that X vector, Y random variable, they're all real valued. Okay. So eventually we will derive the complex valued version of this. It's very similar, but it's a little bit different. We have to put conjugates somewhere, as you can imagine. So we will be attacking that complex valued case in a little bit of time. Okay. So what is our example? Next example is, okay, I would like to illustrate the application of this rule, essentially. Now I'm assuming that x of n, this is my nth observation, c plus w of n, where c is a zero mean random variable, okay, and wn is IID, it's not IID, sorry, it's independent Gaussian random variable such as n0 sigma wn square. Okay, so wn is also zero mean. Its variance is sigma wn square, and that is it. So let's say that I have n of these observations, n from 0 to n minus 1. Okay, so is this clear? So this is a random quantity, observation. This is another random quantity, desired random variable. And this is noise over desired random variable, and I'm observing this noisy desired random variable. Okay? So what do I mean by random variable? For example, okay, so what's our task? Find linear minimum mean square error estimator for C. Okay, that is our task. So how can I, let's say, think about this problem? Well, let's assume that I have such a model, maybe a communication type of model. Let's say that C is equal to -1 and 1. Okay, so with, let's say, equal probability. This is just an example. Clearly, then C will be a zero mean random variable, and its density will be something like this. 1 minus 1 FC of C. Okay. And I have 1/2 as the probability. They are the weights of these impulses. Okay, so if I have, well, such a C, then what's my observation? So my observation is the noisy version of this. So if I have, let's say, the nth observation. So as you see, I'm trying to understand the problem right now. Okay, so can we sketch the density of this observation over here? Even though we don't need to sketch the densities, at the end I will solve this equation system and construct the estimator, but let's try to understand this problem. So there is an inherent assumption, this should be made explicit. So we are assuming that C and, well, this is important actually, WNs are uncorrelated. Well, let's assume that for the sake of this density drawing, that's the independent. Okay. Well, this is a very reasonable assumption because this is my desired signal, -1 or +1. Maybe it's like we are transmitting one bit of information to the other side, and there is some channel noise over here. Okay. So if C and W are independent, what is the density? What is the density of observation? Well, you can remember that density is nothing but, the resulting density is nothing but convolution of this with this Gaussian density. Okay. So then it will be 2 Gaussians added up. -1, 1. Okay. So this is x of n. So if I write this with this independence assumption, so this is FC of C convolution with FWN of WN. These are the random variables. Okay. Very simple. So this is called mixture of Gaussians, as you see. So what's the meaning of this? So in this experiment, let's say in the nth observation, I see something like this. Let's say this is 1.2. So how can 1.2 become this observation, nth observation? The issue is this. C can be 1, obviously, and noise can be 0.2, then this will be shifted to 0.2. Or C can be -1 and noise can be 2.2. When you add them up, this. So the question is, now among those two, how would you estimate C? Of course, we'll be constructing a linear estimator. So I'll be just linearly combining my observations and deciding on the value of the C. Okay, something like that. So this is our task. Of course, this won't be the optimal estimator. The optimal estimator will be the nonlinear estimator, MMSE estimator. But for the sake of, let's say, simplicity, we have this. Okay, so that is the understanding of this problem, let's say, a communication problem. So how can I solve this? Now let me write my observations in vector form. x1, x2, xn. Okay. Well, what else? Now I need to form this Rx matrix. Okay. Then let me try to find this Rx matrix. Rx matrix is expected value of X transpose. So what do I have for that Rx matrix? Well, how can I calculate that? Rx matrix over here. So you may say this is the expected value of x1 square, expected value x1, x2, expected value of x1, xn. At the bottom end, I have this, and this is nothing but outer product of two vectors, and when I take this expected value, I get the entries as pairwise product of every entry of this vector. Okay, very good. So I need to take these expectations. So how can I calculate those expectations? Well, let me see. Then let me move over here. Then Rx's okay, let's write this, or let's try to keep this as it is, because I don't want to write this big matrix again and again. So this is one of the tasks. Then R xy, let me write in this form, the right hand side of this equation system is equal to expected value of x1, x2. Oh, this is, let me start this from 1 then, because, okay, let me have, because I have started from 1 to n. I have started from 1 going up to n. This is up to y. Okay. So once I calculate those two, I am done. So let me calculate, for example, this one. xn times x1. So what do we see? Expected value of, this is c plus wn, then c plus w1. Am I right? Okay. So this is equal to expected value of c square, since all of the other terms are equal to 0 after we take the expectation. So what are the other terms? The other terms are expected value of c times w1, c times wn, plus this is c times w1 plus wn w1, and I have that. So we have said that, well, these are uncorrelated random variables, okay, or if they are independent, that implies the uncorrelatedness. So because of that, this is equal to expected value of c times expected value of wn, and both of the c and wn, for every n, small n, they are all 0 mean, so all of them are equal to 0. So that is it. So I can write this one as sigma c square also. That is the variance of the c, because c is 0 mean, and this is nothing but variance of the c plus mean square, isn't it? So I have that. Okay, so how about this one? xn of n. Well, only difference is instead of 1 over here, I have n also over here and over there. Okay, so this one with n over here, it will be equal to 0, but this will be wn squared. So you will see that this is equal to sigma c square plus sigma wn square. Okay, because if this one is replaced by n, I have wn square, so that makes it the variance of the wn, which is end noise. Okay, capital end noise. Okay, very good. Now, so all of these entries are right now filled, can be filled by similar consideration. Now how about this? x1 times y, or let me say xn times y. So this is, let's use this one, x1 times y. Okay, but y is equal to, over here, c. This is a desired random variable c. Okay, I'm trying to estimate c. So this is equal to x1 times c. Okay, so x1 is this, times c is again sigma c square. Okay, so I have for this one something like that. Okay, then it seems that I can write every entry of the matrix on the left side of this equation system and every entry of this vector on the right hand side. Okay, so let me do that. So then if I do this, I have W1, W2, Wn. Okay, so this one is sigma c squared W1 square, and this one is just sigma c square. Sigma c square. Sigma c square. That is it. And let me write one of them, let's say sigma for the kth one. Let's say somewhere in the middle. Sigma c square. This is equal to right hand side is, it's always sigma c square. Okay. Okay. That is it. So if I can solve this equation system, I am done. I will be getting this weights. That will be the end of this problem. Okay. So as we have said, in all of these calculations, we have assumed that desired signal, which is C, and noise, W, we have assumed that they are uncorrelated, and this is a typical assumption. That is, noise does not carry any information in the sense of correlation. Noise does not carry information about desired signal. That's the reason that we call it noise, okay? So that is not related with the signal term. Okay, so that's the end. So how can I solve this? Well, one thing that we can do at the beginning is, maybe I should divide both sides by, or multiply both sides by 1 over sigma c square, so that I get rid of this, complicated right hand side, or this matrix entries, there will be ones instead at many places. Okay, so that's a good thing to do, but what else? Let me also define the following. So let me define over here SNR. So this is signal power at kth observation. So this is the kth SNR divided by noise power at kth observation. So what do I mean by this? Please remember, kth observation is C plus WK. This is obvious to the signal. This is obvious to the noise. Okay. So what do I mean by power? Well, this is in electrical engineering, you may say this is like the average power. But averages in terms of expectation. So I'm considering C, some kind of a voltage value. So it's like voltage square divided by R will be our, power dissipated over a resistor. Okay, something like that. Okay. And we have this. This is this. Okay. So, okay, if I do that, what do I have? The SNR definition. So let me write this matrix over here after this, because I want to save some space. So these are the optimal weights for linear MMSE estimation. On this side I have just ones because of this division by sigma c square, and over here I have 1 plus 1 over SNR 1. So as you see, once I divide by every entry sigma c squared, I have 1 plus 1 over SNR 1 because it's the reciprocal of this. Okay. All other entries are 1, 1. Let me erase this because it will be all 1. So this is 1. 1 over SNR 2. Let me write a little bigger. Sorry. 1 plus 1 over SNR 3, 1. So this goes up to here and so on. Okay. Or let me again write over here 1, but let me assume that I have this indicate arbitrary SNR K and 1. Okay. So this is again, this one is, let's say, the kth row. Okay. So there is some other rows over here, some other rows, and so on. Okay. That is it actually. Okay, so how can I solve this equation system? That is the end, okay, with the SNR definition. Now the equation is a little bit simpler looking, but how can I look at this equation system? So let's check kth equation. So what do I have in the kth equation? So this is nothing but this vector, inner product with this vector, isn't it? Plus is equal to 1. Am I right? Because as you see, inner product of this vector with W vector S, so every entry S containing a 1, well, forget about this one. So this is the inner product of all 1 vector with W vector, which is this. Plus, the kth entry has an additional term, 1 over SNR K times WK. And that is supposed to be equal to, that's 1, this is this one, okay, over here. So every equation is in this form. So let me solve for, let me call this the sum of the weights. Let me call this S, okay. Then from here, I get WKS. So I have WKS 1 minus S times SNRK, okay, kth SNR. 1 minus S, the sum of all of these weights, times this. So what we observe is the following. Kth weight is proportional to SNRK. So if I increase this SNRK, then kth weight increases. So that is the case. Okay, so there is this proportionality. Of course, it's a little bit more complicated because there is this S factor containing WK also, but let's see. Okay, then how can I solve for WKs? Well, if I sum up all of these W's, so what do I have? I have 1 minus S summation of SNR K. Am I right? If I sum all of them up. So why am I summing them up? Because previously I have called this sum as, S. This is this S. Okay. Now I can solve for S, as you see. Solve for S, and then we will be, let me use this part. Okay. Then I have over here S is equal to, so there is constant minus this term. Oh, that constant is not 1. So S is equal to summation of K1 to N SNR K divided by, is this correct? S plus this. SNR K. Okay. Let me check in case I make a mistake. Okay, it looks correct. So I get this S value. So once I get this S value, then WK is equal to 1 minus S times. So as you see, once I get the S value, then WK is fixed. So we are done with this then. Which is then SNR K. Okay, it's not increasing linearly, but what I see is that if I, for example, double SNR K, then numerator is doubled, but there is also some effect over there in the denominator. So what did we see? So for the solution of this equation system, I have recognized that this equation is instrumental for our purposes. Okay. So this is a critical variable. You may say this is like an auxiliary variable of this problem. Once I solve for this auxiliary variable, WKs are fixed. Now I can express WKs in terms of this auxiliary variable. Then I use the definition of the S and solve for S. Okay. So I'm just hunting for S, as you see with this step. Then once I find this S value, 1 minus S, if you multiply this by minus 1 and add 1, as you see that 1 minus S is this 1 times this. This is 1 minus S, this part, but let me erase this. Times SNR K will be the kth weight. Okay. So what are our weights? Now our weight vector is, let me write its transpose because of this space limitations. SNR1 divided by 1 plus, let me write sum of WK SNRs. SNR2 divided by 1 plus summation of SNRK. So nth weight is SNR N. So does this make sense? So once you do a calculation, you should always stop and think whether this makes sense to you or not. And you should check, some obvious cases. For example, if SNR of the first observation is equal to 0, meaning that, how can this be equal to 0? This can be equal to 0, or this can be infinite, or it's, let's say, very small, meaning that the kth, the first observation noise is very large. Then, this is a very small weight, isn't it? Okay, because you can see that this denominator is constant for all of these weights. If you compare this weight with this weight, the ratio is the SNR ratio, as you see. So if SNR1 is very small, then the first weight is very small. So that makes sense. So if, let's say, one of those SNRs are infinite, so what happens? For example, the nth one is infinite. If the nth one is infinite, then on the denominator I have infinite. Then all of these are 0, because at one point this is SNR 1 over SNR N. Okay, 0, 0. So I'm left with this. So this is SNR N is infinite, and in the summation I have SNR N. Their ratio as SNR N goes to infinite will be equal to 1. Okay, that also makes sense, because then this linear combination weight gives all the weight to the observation with the infinite SNR. Okay, that is also good. Okay, so what else can I say? Well, let me calculate the mean square error for this. So how do you calculate mean square error? Let me write this. Minimum, well, actually this is minimum value is, so expected value of y square minus, this is W transpose times RXY, okay? So let me also, last time again we have derived this. So let's calculate this. So what is our estimation error variance at the end of this calculation? So this is equal to expected value of y minus y hat square with, you know, optimal W, where W are optimally selected. I think it is clear. So this is minimum value for the linear mean square error estimation problem. Okay, so this is directly from here. Let me write it one more time. Expected value of y squared minus this times RXY. Okay. So in our case, y is equal to c, desired variable is equal to c. Okay. And then let's remember, this is then sigma c square, because c square, expected value of c square is sigma c square minus W transpose times RXY. RXY is actually this vector. So this vector of ones, but let me write sigma c square times ones. Let me make it like that. Okay. So this is my, previously we have calculated this RXY vector. X is vector, y is the desired quantity. Okay. Now if I do this, again this is simply sigma c square 1 minus W transpose times 1. Okay. But W transpose times 1 is, it's just the weight of this. So this is sigma square times 1 minus S. Okay. Because as you see, this is S. And then this is sigma c square, because I have calculated 1 minus S over here. 1 over summation of all SNRs. Let me write this a little bigger then. Okay. So this is our linear minimum mean square error value at the end. Okay, that is it. So this is this. Okay, so what can I say about this result? For example, if one of those SNRs are infinite, again I see that my error will be equal to, error variance will be equal to 0. Okay, according to this is my error, it will be equal to 0. Now here's a question. Let's assume that I have, let's say, n observations, n of them, capital N observations, each of them have SNR of, let's say, 1 unit, one SNR of 1, okay? So would you prefer to have n observations with SNR of 1 or a single observation with SNR of n? Well, it's an interesting question. So how can I answer that question? Maybe I can calculate this linear mean square error result, okay? So according to this, we see that it doesn't matter how many observations you have, because for the linear minimum mean square error result, we see that the summation of all of those SNRs are important. So we see that the sum of the SNRs is a critical value. So if somebody can give me a single observation with a good SNR, maybe that's good enough for my purposes. Okay, so this can be useful in designing a system. Maybe you are optimizing the number of observations, isn't it? So if each observation costs, let's say, some time or money, whatever it is, then using this, you can optimize the number of observations in terms of SNR. Okay, there is always an engineering trade-off, something like that. Okay, so what else? Let me see. Okay, so that is it for this example, but now let me solve a very similar example, but I have to first find it. Let me see. Like this. So should I keep these matrices? But before that, let me do this. Okay. So let me have a second example, but it's very close related. Now x of n is c plus w of n, but c is, let's say, non-zero mean. C is, let's say, Gaussian distributed. Distribution is not important for our purposes, but there is mu of c and sigma c square, and w of n is as before. So they are, let's say, uncorrelated random variables, and this is defined like that for every n. Okay, it's the same problem. So I have observations, this. So what is the difference? Previously we had a zero mean case. Okay. Now mu c is maybe not equal to 0. Okay. So over here, this is the mean value. Maybe it's not equal to 0. Maybe it is equal to 0. Okay, it's a generic variable. So the interesting cases, of course, previously we have solved the 0 case. So what should I do with that one? Now again, I can define the same method. I can define an x vector. So x1, xn. Then I should write rx. Okay. So in this rx matrix, I need to have, let's only find one of them, x1 square. I think it's clear, we have this matrix. But in the x1 square, now what do I have? It's the square of this for n is equal to 1. So I have expected value of c square plus expected value of w1 square, am I right? So I have sigma c square plus mu of c square plus sigma w1 square. Oh, I see. Now it's okay. So the case is the following. Wherever I see this sigma c square, I'm changing this matrix right now. I have to change it. Then I'm replacing with, with this sigma c square plus mu c square over here. Okay. So at everywhere I have to do that. Then probably I will divide by sigma c square plus mu c square and so on. Okay, that is the change required if you repeat the same steps. But let me do it this way. Now, maybe if I call this okay, if I update my SNR definition for this with the mean problem, so this is, let's say, SNR, let's say, hat for the kth observation. If I update it as, what should I do? If I update this expected value of c square divided by wk square, then I have sigma c square divided by, sorry, mu c squared, sorry, this is wk, sigma wk square. Okay, if I have this updated SNR definition, then what happens? Well, this matrix, for every sigma c square, I have an additional mu c square term. Okay, so if I divide by every sigma c square is replaced by this, then exactly again I'll be getting the same matrix. Okay, so if I do that, no problems. All of my earlier results will be valid with this SNR definition. So nothing changes, you may say, only the SNR definition changes, isn't it? So this is the anti-SNR. Okay. So this is the same equation system with this SNR definition. So the solution is the same, but with this SNR definition. So this is SNR of this second case, SNR with hat. Okay. Where I have included this one. So all of these results are then identical. So what is my y hat in this case? Well, I know this W's. W transpose times X. So this is equal to kth SNR times my kth observation divided by SNRK. Okay, because this was previous to my kth weight, please remember. Now it's again the kth weight, but with this SNR hat definition over here. So this is my kth observation. So this is the inner product of kth weight and the kth observation is this. Okay, that is it. Well, now question is y hat for this problem. What do I mean by y hat? This y hat for this problem results, or does y hat for result in an unbiased estimator? Well, you can see the following. Let me answer. Expected value of y hat. Expected value of y hat is, well, then this wk times, what's the expected value of x vector? Expected value of this, or you take the expected value of this, then the expected value of the kth observation is kth observation is just mu of c times 1, or let me write, okay. So what do I have? This is times W transpose of 1. Okay. So is this equal to expected value of C? That is the question. Which is this mu C. Okay. So that is what we have as a question. So what we see is then as follows. Let me keep this, let me write it over here. So if W transpose times 1, which we call S sum, is equal to 1, then estimator is unbiased, but in this case, well, what is the summation? Well, if you check the summation, I have, let me also, this is WK, okay? In this case, summation of all WKs is equal to this part actually. Summation of SNR K 1 plus SNR K and is not equal to 1. Okay. So estimator is biased. Okay. That is one of our results. So we see that if mu C is non-zero, then the estimator is biased. So how about the case? If mu C is equal to 0, then this equation is always satisfied. Because 0 times a number, then linear MMSE is unbiased, also in this case. Okay, because you see that once you do this calculation, then if this is 0 mean, then this equation is always satisfied. Maybe it's easier to see from this. If observations are all 0 mean, then their average is also 0 mean. And if this 0 average matches the desired signal's mean, which is 0, then the estimator is unbiased. Now here's a question. Okay. So we have seen that I have this bias in my estimate. So let's try to remove the bias by including another, let's say, artificial, let me put this, observation, which is just 1. Okay. So what do I mean by this? So let's say that this is my new x vector. My new x vector is, I'm talking about this vector. Now it's composed of my observations. And at the end I have x of n and I have 1 over here. Okay. So we have solved a similar example before, but my goal is right now construct an estimator as follows. Now it will be W, let's say new, with one more dimension. This is right now n plus 1 dimension. N plus 1 times 1. Okay. So W times this x new. And you can see that this is nothing but linear combinations of observations plus another term, plus its constant term because of this. So this is W, let's say, n plus 1. Okay, so this is what we call right now an affine estimator, not a linear estimator anymore. Okay, so the last one is 1 is multiplying this, the last element of this. So this is W new weights according to this. So I should, repeat the same calculation. Now I have 1 over here. I should do all of those calculations one more time, and should I get that result? Okay. Well, I don't want to repeat those calculations again and again for this simple problem. So what can I do? So instead of doing that, do you remember I always keep saying the mean values are not so critical in our problems. So what do I mean by that? So let me define, let's say, x new as, let me put an head also over here. So x1 minus, let me see, mu of c, x2 minus mu of c, then xn minus mu of c, and 1. So what do I mean by this? If I define my observations like that, in other words, from every observation, I'm subtracting a constant value. So subtracting a constant value from every observation. Okay. So can I do this? Of course I can do that. Now please remember, x of, let's say, k is equal to, this is c plus w of k. Now c is equal to, let me use this color. So right now it has a mean and variance. This is nothing but as before. Okay, I have that. Well, if I subtract this, and if I call this my new observation, which is the first one, new 1, let's say, with this hat, the first element of this. Okay, can I do this? Of course I can do that. But what is the purpose of that? The purpose is as follows. Given this observation, I'm subtracting this mean. Now I will be calling this a c, let's say again, hat, according to the c hat. So what is the, well, n 0 sigma c square, because this right now is 0 mean Gaussian random variable with the variance that. And how about this one? This one is exactly like that, no problems with this. Okay, there are no changes over here. So as you see, by doing this, subtraction, I end up with my previous model for which this is valid. Because this is, okay, this is the kth observation. This is the kth observation model. So I see that in the kth observation model, I have a 0 mean random variable with this variance and noise with this variance, which is this equation system. So only difference is that right now this is n plus 1 dimensional, isn't it? N plus 1 times 1. But this matrix is obviously n by n, because I'm only finding this w up to wn, but I have a new weight right now, wn plus 1 for this bias. Okay, I would like to calculate this bias. So how can I do this? Well, you will maybe immediately see, but let me explain it somewhat. So if I do this, then expected value of, again doing this calculation, I'm trying to find this optimal weights, x new hat, new observation vector with mean subtracted, times x new hat transpose is equal to what? Is equal to this matrix, okay? So this is m plus 1 times m plus 1 dimension, okay? Well, let me write this equation system, not the matrix, times I have this weights over here, w1, wn, wn plus 1 is equal to right hand side, okay? So this is expected value of, we have x new hat, this vector, times desired quantity, which is c in this case, c. Okay, I have that. Okay, let me try to find the entries of this. Now, this is 0 mean, 0 mean, 0 mean. Well, no changes up to here. This matrix is, this part of this matrix, m by n part, over here, is exactly this matrix. So why do I say so? Let's calculate. X new 1 parentheses square is square of this, okay? Then you get the sigma c square. So in this observation model, you have parentheses square of this, you have two terms, C hat plus WK. So what is the parentheses square of this after expectation? You have sigma C square plus WK square. Look at this. That is exactly the same thing. Only difference is that previously I was calling this C hat variable as C, and it's the same result that we have done earlier. Okay, there are no changes over there. So only difference can be, well, how about this part of this matrix? So that is, let me write expected value of x1. Am I right? That is the expected, well, the reason is, oh sorry, that is the expected value of x hat new vector and the first entry of this. Let me write it like 1. Okay, over here. Because that entry, the upper right corner of this matrix, is nothing but the product of this and that after expectation, x, this and that, and this is equal to all zeros. So I have 0 for this. So I have all zeros over here. Because this is already 0 mean. Okay, if you check this, x1 minus mu c is 0 mean. Okay. Then this part is the same. This part is, so the first n equations are the same as you see. So this part is corresponding to this part. This is, let's say, n by 1 part. Corresponds to exactly this n by 1 part. Okay. So then let me look at this part. So how about this entry? So this is expected value of, actually this is the transpose of this, but okay. X, this is 1 times x new hat of 1. Okay. So this is the last column, last entry times this. Last entry times the other one will be the next one. The next one, and so on. And all of them are again equal to 0 because of this, you know, this matrix is supposed to be symmetric, right? That's, so I'm left with only this part. Okay. So what is that one? That is over here. Let me write it with again the same. So over here I have expected value of this entry times the same entry, expected value of 1. So this is then 1. So as you see, I copy and paste this matrix over here, make up zeros over here, and I insert only 1 over here after this kind of a mean subtraction. Okay. Then what do I have over here? So this part of this matrix, again a copy-paste operation. You copy this black vector, black colored vector over here, and we are left with this. So what is this? Last entry times C. Last entry times C is expected value of C. So this is the mu C. So what do I see? I see the following. Then we see that we see that W1 of this new system, W2 of this new system, and up to Wn of this new system is exactly as before, because it's the same equation system. That is Wk, as far as I remember, proportional with SNR K divided by 1 plus 1 to n SNR K and Wn plus 1 right now of this new system, of these weights, these are the new ones, okay, is equal to just mu c, okay, because it's the same equation system. First n rows are identical, and in the n plus first row I have, you know, this weight is equal to mu c, that is it. Then you may say that what is the change? Well, the change is right now y hat is equal to w of this new system weights times of this new, let me say this like a new vector, this, then this is equal to so this is one of them. SNR K times that is it. Or let me write plus 1 times mu c. Okay. So what's going on? So this is my WK of this new system. Which is the same as before, okay? So this new weights inner product with now these observations, of course, noise subtracted observations. And I have such a case, okay? So this is the noise subtracted. So this is x new hat of the kate, let's say kate 1. Okay, it's this one, okay? So I'm talking about noise subtracted version like that. So how about this? So this is W and, sorry, this is W n plus 1 of nu. Okay, mu c. And this is multiplied by, you know, this is the last entry of this, just multiplied by 1. Okay. So as you see, by artificially generating this, let's say, observation of 1, now I am ending up with this kind of an estimator. But what is the property of this estimator? If you take the expected value of y, then expected value, this is 0 mean. Expected value of xk minus mu c is equal to 0. Expected value of y is equal to expected value of c. So this is indeed an unbiased estimator. So this becomes an unbiased, it's an affine minimum mean square error estimator. Okay. So what we have seen that there is some freedom in the selection of these observations, as you see. Of course, I could have multiplied the kate observation by 5, and I could have written 5 over here, isn't it? 5 times the kate observation. So if it's helpful for my purposes, I can always do that, but I doubt that it will be helpful over here. So you see that, well, I can even add and subtract these observations if I wish, because at the end this linear combination idea finds the optimal weights. Later on we will interpret these random vectors, these observations, random observations, these observations as our elements of vector space, okay, immediately, maybe in an hour or so, okay. So this is nothing but a linear combination of the elements of this vector space by this W operation. Okay, I'm linearly combining elements of this vector space according to this. Of course, you know, I can multiply one of this element by 5, then of course this W weight will be, let's say, divided by 5. If it can be divided by 5, then I will be getting exactly the same results. So the idea is there is some freedom in the combination of these observations. Right now over here I have added this 1 and subtract this mu c times 1 from all of these observations, and of course this results in such a simplification. And this is helpful because why it is helpful? At the beginning I have assumed the 0 mean case, so without dealing with mean, At the end, including the effect of the mean, I can end up with such an estimator, okay? Maybe with some less computation. So as I have said many times, mean is not very critical for our purposes. You can get rid of the mean at the beginning of this calculation and assume a zero mean quantity, and at the end you can compensate for the mean, if the estimator, of course, enables to do that, okay? And that's all for now, so we will continue after a break.